So as we're getting ready to stream our program tonight, maybe could ask you a couple of questions, get a show of hands. How many of you heard about this program tonight through our website initially? Okay, about 4 of you. How many of you received an electronic invitation from someone? Quite a few of you. How many of you have been to our programs in the past? All right, about 2/3. Okay, great. Those of you that are new here, how did you hear about the event? Pardon? Through a friend? Yes. Okay. Good evening, everyone. Welcome to the Vancouver Aquarium. Thanks for coming tonight. My name is Jonathan. I've brought up the wrong set of notes. So, why are we here tonight? We're here because the world's oceans are rising. Many of us are concerned how this will affect our coastal areas. Will coastal cities be underwater in the future? Where will the waterfront property be in 20 years? Will fish be swimming down the streets? Whatever your questions, tonight's program, Rising Seas Update, the latest IPCC projections and more, will give all of us some factual information about what is really going on with our growing oceans. To introduce our speaker tonight, Dr. John Nightingale, President and CEO of the Vancouver Aquarium.
Thanks, Jonathan, and thanks to all of you for coming. So our guest speaker tonight is an interesting fellow. He's an oceanographer, a consultant, an author, a diver. He has a broad background in marine sciences with degrees in geology and economics, neither of which you might know to marine science, but he has a lifelong work experience in the marine environment. And that background allows him to see the big picture on climate change and to look ahead at some of the large-scale financial, environmental, and societal impacts that are coming, particularly related to sea level rise. He's been a leader in both the private sector and the nonprofit world. He served as the CEO of the Cousteau Society for some years and the International Seakeepers Society. Since he wrote the book, which was published about a week before Hurricane Sandy inundated the East Coast, he's been in the media, I think would probably be the understatement of the week. He's a fellow of the Institute of Marine Engineering, Science, and Technology, a member of the Explorers Club, a member of the American Geophysical Union, the American Association of Advancement of Science, and so on. So I think we're in for a treat. I know from having seen and listened to John before that we're going to learn a lot, but it's going to be completely enjoyable, and any of you who have shoreline waterfront houses will immediately call your realtor. John Englander.
Let's turn this on. I guess it's on. No. Is that on? And this on too? Okay. Well, we've got 2 different mics here, I think, for the stream. Thank you. It's great to be back. Uh-oh. That's not good. Jonathan, is this okay? Should one of these be off or?
We'll take this one away.
Okay. It's great to be back at the Vancouver Aquarium. I've been here many, many times over the years, and even in the midst of a major expansion program, which is a bit disruptive, it's still nice to come back here. And in fact, I really appreciate that John and Dolph and Jonathan and the staff here are not only upgrading the aquarium physically, but they're doing more with information and outreach to bring information about the oceans to other communities too. And I think that's part of their exciting expansion plans. And streaming this tonight is one example of that, kind of taking technology and looking at ocean and ocean education differently. The map of the world comes in different forms. Often we look at it as a globe, but you can only look at one side of it at a moment then. And so this rendition is useful without the clouds. It reminds us that, of course, the most important feature of this planet is the line between ocean and land. That defines real estate, it defines where we live, it defines communities, it defines everything from harbors and shipping and issues of estuaries. It is the most important geologic feature on the planet, where the land starts and meets the ocean. And it's about to change. In fact, I would say that it's actually already started to change. And what I want to do tonight is help you see it a little bit differently. There are several different ways that the shoreline changes, and we tend to confuse them. So let's just get that out of the way first. There's, of course, a hurricane type event. Sandy, as John mentioned, came out, or happened the week my book appeared in October 2012. And this was a breach of the shoreline. And it was a combination of not only a 6-foot storm surge because of a 1,000-mile diameter hurricane, a record hurricane, but then a funneling of the water because of a geologic feature there in New York, New Jersey, and the shallow eastern shelf that you don't have out here, but that can pile up the water 50% more. And that's primarily what it was. It also hit at a rather extreme tide. You know, every day we have high and low tides, and certain days of the month when the moon phases are right, we have an extreme tide. And then at certain times of the year when the planets line up, we have an extreme tide, if you would. And this was a moderately extreme tide, which made the impacts even worse. But just those extreme tide events, which you call out here in the Pacific typically king tides, I believe. We don't use that term in the East Coast. But king tides from Seattle here to Australia are flooding streets without rainfall. They're flooding streets without storm surge. Predictably, every month from Miami to parts of San Francisco Bay to, literally every coastal community in the world during those days of extreme tide, to Delta right down here in the area of Vancouver, just south of here. It's predictable. The days we have extreme tides, the streets flood. And that didn't happen a few decades ago. The moon hasn't gotten any closer. There's another reason. The ocean's getting taller. And we need to look at that and kind of pull it apart, because it's easy to see those things in combination. And it's becoming a problem when cars are driving through salt water on streets once a month and their wheels are rusting. But people don't recognize it because it's like that proverbial boiling the frog. It happens gradually and you don't notice it, as they say, even though that turns out not to be true. But different factors of ocean height add up, from sea level, then daily tides, extreme tides, storm surge. They all add up to the vertical column. And for each foot or meter, whatever you wish, of height, the average ratio globally is for each foot of height, it moves inland 300 feet. 300-to-1 ratio, global average. Here it's probably a little bit less, but flat areas like Florida, it's more. But it just shows you the scale. We tend to hear about a foot of sea level rise or a few inches and say, well, that's not too much. The problem is it's the horizontal movement. But here's the thing that very few people think about, and we're going to now shift from all the other causes to sea level. The difference is that a storm surge and an extreme tide recede, and you can rebuild. And while they combine and add on top of sea level will not recede for centuries, actually for more than 1,000 years, because the ocean's warmer. Before we proceed, I'm going to do a quick little quiz. I did this last week in Florida and 2 weeks before that in San Diego. I'd like you to choose one of 3 answers to this question. If we look back in the last century, and I have to be very specific here, the last century, that the increase in sea level would be dominantly because of one of, I'm going to give you 3 choices. Show of hands, okay? The first choice, I'll give you all 3 first so you get them. The first choice is the melting of the polar ice cap around the North Pole. The second choice would be that seawater is expanding for some reason. And the third choice would be subsidence of land, okay? That the land has gone down. So those are your 3 choices. I'm sorry, and I'll give you a 4th. I knew there was one I was missing. The glaciers. The glaciers are melting, which of course we're all aware of in different places. So which of those 4 factors is the dominant cause of sea level rise? Yes? 2. Well, wait a minute. I'm going to let everybody vote. Would you make him pay attention? Okay. I want you by a show of hands to decide which you think is most dominant, okay? The first one is melting of the polar ice cap. Second one is thermal expansion of seawater. The third is subsidence. And the fourth is melting of glaciers. First one, how many believe it's melting of the polar ice cap? Okay, now I can see. Second is thermal expansion of seawater. Oh, it's a smart crowd. Okay, we don't have to do the rest of it. Okay, that happens to be the right answer. Now let's talk about the other myths. We've already nailed the first one. The polar ice cap, which is floating sea ice, as obviously you all know. You're a very learned audience, by the way. I don't think I've ever had that result before. Most people, I would say 90% of people, believe that the melting of the polar ice cap is why sea level is rising. It's not, of course, as you know. A second misconception is if we're just green enough and sustainable enough and do the right things and reduce our energy consumption, we can stop sea level from rising. That technology, which we all embrace and is so great in so many ways, that technology holds the promise to stop sea level rising in the short term, in the next few decades or century. That's also a myth. We'll talk about why. That seawalls in places like South Florida and the Maldives and coral-based islands where this porous limestone could stop seawater from coming in. It can't, because the water travels in through the rock. It's porous rock. Some places seawalls will work. And it's just a natural cycle. It's happened before. Man doesn't have any significant impact. Common myth. And we've already disputed that it's similar to storm surge and extreme tides. It is in some ways, but it doesn't go down. It's a one-direction movement. Really important difference. And again, we can be concerned about the polar bears, and we can look at the disappearing ice in the Arctic. It doesn't affect sea level, but there's two really important lessons that can be taken away from the disappearance of the polar ice cap. It proves the warming. If anybody says, well, you know, this is cycles and 17 years ago this or that or the other thing, the Arctic is going to be ice-free some September in the next decade or two at the most, perhaps 3 or 4 years from now. And for each year succeeding, it will be for more days, typically. But over the next decades, it will increase the number of ice-free days in the Arctic. That's significant enough by itself. But when you put in context that the Arctic's been frozen for 3 million years, you get a sense that we're in a different era. And this is not just another cycle. And we want to talk about that because it really puts it in context. The other thing that's really important, besides the profoundness and the uniqueness of an ice-free Arctic, is that as you go from bright white ice to dark ocean, the planet absorbs more heat. And most of you, I suspect, know that too. And that's a really important factor. It's one of those positive feedback loops, things that accelerates the warming as you change the planet's reflectance, in effect, as the ice disappears. And again, this has happened in a natural cycle. We're going to look at in a minute how it's changed from a natural cycle to now this phenomenon that we've triggered. You get a sense of the problem or the potential of sea level rise by looking at a map like this, and the ice on land, Greenland and Antarctica, and a little bit of glaciers around the world, that's the dominant cause or potential for sea level rise. Now, it's not all going to melt this century or next. Let's not panic, and the idea here is to be honest about it. We have a real problem. There's no point in scaring people, and there's no point in minimizing it or deluding ourselves or burying our head in the sand. Because this is one problem that isn't just one of those things up there in the atmosphere that's hard to get your hands around. This affects the shoreline and real estate. So it's different. And it's either different because some of you live on the water and are here because of that, and you're concerned about that. But it's also different because it allows us to see climate change, which is a bit of an ambiguous thing because it may be warmer here or colder there, or more rain or more drought, and it's a little bit confusing. But the sea level changing, moving the shoreline, is unambiguous. To put in perspective the magnitude of what can happen, if all the ice remaining on the planet melts sea level will rise another 65 meters, 212 feet. Again, it will take centuries and perhaps thousands of years, but it gives you a scale of what the enormity is. But interestingly, glaciers, which are melting away very quickly, they only account for about a meter of that 65. Greenland would be about 7 or 8 meters, and Antarctica's pretty much the rest. So sea level facts to counter the myths. The truth is that the ocean level proves long-term climate change, those long-term shifts in pattern, because as the planet's average temperature changes, the ice sheets change, and you can see the ocean going up and down. And I'll show you that in just a minute. It's been pretty stable for 6,000 years, which happens to be the period of human civilization on our written record, and pretty well explains why we tend to be in disbelief that it could rise much. The natural cycle that some people refer to but have no clue what the natural cycle was, the Ice Age cycle, is roughly a 100,000-year cycle. It's been going on for millions of years. And now sea level is moving up, and we're going to see that it's actually broken out of the natural cycle, which is a very telling insight and fact. And which leads us to the bottom point here, that we've not just accelerated climate change and the melting of ice, we've actually changed the cycle that was a natural one. And that's, I think, the most profound conclusion of all. But we're going to get beyond all that and talk about what can we see ahead, because we all face difficult news, whether it be medical or personal or financial, about the world in many different ways. This one's unique, and we need to start looking ahead to it positively. To put things in perspective, Florida, where I happen to live, becomes a very graphic state to just illustrate how changing sea level can really change things. Looking at Florida today is a very familiar shape on the left. 18,000 years ago, when sea level was down 120 meters, the peak of the last ice age, Florida was much bigger, 100 miles wider because of the shallow bank. Conversely, 120,000 years ago, at the similar warm spot of the last ice age cycle, sea level was about 8 meters higher, and Florida was much smaller. Sea level has risen, this is since 1850. It shows what's happening in the recent century or two, century and a half. And the rise in sea level is about 18 centimeters, 7 or 8 inches for anybody in that system. The line has some wiggles in it, but it's a pretty straight line. Actually, the trend is starting to accelerate. The little red line at the upper right, which is the satellite data as opposed to the old tide gauge data. This is global average. One of the really important things about sea level is that it varies surprisingly. That same 8 inches of global sea level, or 18 centimeters, is the red wavy line toward the bottom. And here are 13 US cities to show you how it can vary in that same period of time that it was a global, permit me to do inches here because this chart's in inches, between 8 inches of global average ranged from 46 inches on the left outside of New Orleans to 30 inches in Virginia Beach or Norfolk, Virginia, to 14 inches for New York, Miami's 12, and on the far right is below the line is Los Angeles at 4. And the difference is that land moves up or down, uplift or subsidence. We don't tend to see it because, again, it's fractions of an inch per year, but it adds up. And if it exceeds the rate of sea level rise, as it does in Los Angeles, because the Pacific plate is lifting California, sea level appears to be going down. In Alaska, that's even more the case. Alaska has really, and I think the Canadian Arctic would be the same, really a strong uplift because of the glaciers having melted there last, or the ice sheet. And so the land is kind of rebounding. And that either minimizes or actually can overpower sea level rise or be a stronger factor. So when you look at the ocean from Los Angeles, it looks like 4 inches as opposed to 8. And in Alaska, it's going down. To summarize, I think we got that there are natural cycles. We've now broken out of it. There's also the thermal expansion of seawater, which has been a constant as temperature warms. It's just a simple very, very minuscule amount of expansion, about 3 or 4 inches over the last century. And in certain places, the Gulf Stream slowing down, and that is so it's just an example of some kind of weird and minor effects, just to be really, I guess, all-encompassing, but I wouldn't pay much attention to that. The other things, the amount of year to year, there can be change the amount of rainfall, where the rain lands, does it saturate in the ground and stay there, does it quickly run off to the ocean? Those are all kind of variables, but they kind of sort out over a period of years. The biggest change happened during the ice ages, and just to remind us that, and I use the slide from Ice Age 2, The Meltdown, and how many of you saw the 4-part documentary series? If you have kids or grandkids, you probably watched this as many times as I did. But behind Manny and Sid and Scat and Diego is 2 miles of ice, about 3 kilometers. And as that 10,000 feet or almost 3 kilometers of ice melted, sea level rose 120 meters. Makes sense. And here it is graphically. And the 2 interesting things I think to take away from this are that it doesn't rise smoothly, that 14,000 years ago, sea level rose about 20 meters in 4 centuries. That's huge. Like a half a meter per decade for 40 decades on average. And in fact, many people think that accounts for the biblical tales or in the Quran, or even some of the First Nations myths or stories about the flood. But what's perhaps equally important is that sea level got to pretty much the current level about 6,000 years ago, which is just about when we started keeping written records, and most of us would agree is more or less the range of human civilization as we know it, 6,000 or 8,000 years. And sea level hasn't moved much since then, which probably accounts for why we just don't believe it's going to do much. But here's one chart, and I think I've only got one more chart after this, so I'll get done with the graphics. But this chart, some of you have seen before if you've heard me talk, is probably the best single bit of information about climate. It's 420,000 years, sea level in blue at the bottom. In the middle is red, denoting the global average temperature of the planet, showing the ice ages up and down about 5 degrees Celsius, global average. And then at the top is green for CO2, a greenhouse gas. And what's interesting is that there's 4 full cycles here of all 3 of those lines, and they line up. They're not exactly the same. They're not exactly the same from cycle to cycle, but if you just draw a line down through the peaks, they're pretty much right on top of each other. And the reason is that, again, the planet changes temperature through a natural cycle historically. The ice sheets change size, and as temperature goes up, the ice sheets get smaller and sea level goes up. So they go together. And the relationship between a greenhouse gas and temperature, most of you probably know this, but CO2 is an amazing heat trap capacity. A little bit, 1 molecule in 4,000, or actually we're 1 molecule in 2,500 now, means the Earth is about 60 degrees, Fahrenheit, about, I guess that's 35 degrees Celsius warmer than it would otherwise be. We'd essentially be uninhabitable as we know it if we didn't have any CO2 in the atmosphere, besides the biologic side of it. It's that much of a heat insulator. And it's interesting that if you looked at this very carefully, that there are certain times in those cycles when CO2 has risen before temperature and certain times when temperature precedes CO2, which some contrarians or skeptics have you say, one couldn't cause the other. Well, it's one of those relationships in physics and chemistry that actually 2 things can go together. CO2 traps heat, and when the oceans get warmer, they release CO2. So they do go together. It doesn't matter which one starts first. But the interesting thing is that the cycles, do I have a pointer here? Yeah, okay. Can you see that red dot? Anyway, the cycles from the top to the bottom is about an 80-20 split of the roughly 100,000 year cycle. And we're at the normal high point. And normally sea level would be starting down now as we headed 80,000 years toward the next ice age. But in the last 2 centuries, it's the elevation of greenhouse gases, shown there in the top, that's caused a change. And in fact, whereas all 3 lines should have been heading down somewhere this century, all 3 are heading up. CO2 is going up like a rocket. Temperature is 0.85 Celsius warmer, and sea level is 18 centimeters higher. The challenge is how quickly does temperature and sea level continue to respond to incredibly fast rates of CO2 rising. We don't know. The truth is, nobody knows. It's never happened before in hundreds of millions of years, and even if it happened, the rock record doesn't allow us to discern it that closely. So we're running the experiment to see, how quickly, if you warm things up this much, how quickly you can melt the ice and what will happen with sea level. We don't know. We'll talk about the possibilities here in a minute. We get that data by ice core samples from Greenland and Antarctica. Drill down and you get slivers of ice, very much like tree rings. You probably know about this, but the bubbles, the bright spots there are air samples, and you can go in and measure CO2, and isotopes of oxygen will tell you temperature. A little more sophisticated, but really neat. But here's the IPCC. How many of you know what the IPCC is? I need to kind of do this. Okay. About half. That's pretty amazing too. And I thought about that after we titled this. Most audiences would not. So you're a very, again, informed audience. The Intergovernmental Panel on Climate Change, part of the UN, gives a report every 5 or 6 years. The fifth report, they started in 1990. The fifth report just started coming out in September. It comes out in 4 volumes. The next volume comes out this week or next week, actually. But what that report says about sea level is already well known. And it says that we could get 10 to 32 inches of sea level rise this century. In centimeters, I think it's 26 to 82 centimeters, as I recall. The problem is that most people think that what they're saying is we could get 10 to 32 inches of sea level rise, or 26 to 82. And I sound like I'm contradicting myself because of course that's what it says. The problem is you have to kind of read the fine print, like so many things, to find out that they're really not saying that's what could happen. They've been asked a different question than what the world is reading this book to mean. They've been asked a question, what do you know for almost certain, like 90% confidence, that will happen this century that you can put in objective terms and quantify? That's the question they're asking or answering. And the answer to that question is those numbers. And then if you read the text, they say, well, there's a couple of things we can't quite put a finger on here, that we can't nail down. One of them is methane, which is coming out of the ground in the permafrost and various places and is an accelerant. Talk about that in a minute. And the other is there's a place in West Antarctica that has some what are called marine glaciers that we're going to look at in some detail. And the recent evidence, what I'm going to share with you tonight, is that the most recent evidence from Greenland and Antarctica about methane is really disconcerting. It should be a very serious concern, and it's not fully understood by not only most of you in the room, but I've talked to engineering firms, I've talked to government scientists, and most people either don't look at it holistically, they look at some aspect of this, or they haven't gotten through the headline of those figures. And that's what I've been asked to come and explain tonight, and we'll get through this pretty quickly now. I've kind of brought you up to speed. Some of you haven't heard this before. A few of you heard me here last summer. I think up till now it's been kind of a rehash. Methane, according to the latest IPCC book, methane is far more potent as a warming agent than any of us thought. It's often said to be 21 to 26 times more potent as a warming agent than CO2 on a molecule by molecule basis. There's two bad misunderstandings with that. One is that really was referring to over the course of a century, and it degrades very substantially, almost has a half-life. But those figures also turned out to be low. If you looked over the course of a century, now the latest figure is 32 times, but of more concern is in the first 2 decades that it comes out of the ground or seabed, it's 86 times more potent than CO2 as a warming agent. And the fracking operations and the escape from fugitive methane or natural gas or coming out of the seabed, the permafrost, the methane hydrates, the slushy methane that's under the seabed, those are all potentials for a very strong warming. It's hard to quantify, so the IPCC can't put it into figures and notes that, but people don't get to the footnote. The second thing is West Antarctica. The area shown in red at pretty much the 8 o'clock position there are some glaciers either designated by the name Thwaites or Pine Bay Glacier or the Pine Island Glaciers. But there's a couple of glaciers there that we're going to look at in just a minute. And they were predicted in 1978 to be the potential for catastrophic sea level rise. 35 years ago, 36 years ago. They're pretty much on schedule, but we don't know for sure. We've never warmed that quick. It's still just a possibility. It's not a probability. Whether it's a 3% chance or a 13% chance, we don't know. So it's not put in the figures of what we know will happen this century that scientists will put their names on. Now, before we get to looking at West Antarctic and Greenland in detail, and that's really the thrust of the real focus of tonight, the last half of the evening, is let's just look, when I say that the scientific community, the IPCC in particular, who do a great job overall, have a pattern of understating sea level projections. And here's the proof. This is what they did in 1990, different degrees of confidence, different probabilities for what would happen over the coming decades, shown in two shades of blue and some gray lines, right? In 2002, they did it again. And again, they were on record and widely published. This isn't anybody's interpretation of what they said. Projections of what could happen to sea level rise this century. The green bands have narrowed a little bit and raised a little bit, as one would expect 12 years later. A little more accurate. Ice is melting faster and faster, so they're willing to make a better projection. But now we can look back and say, how good were they? The gold line is sea level, the red line is the trend line smoothing out the measurements. This shouldn't be. In 10 and 20 years, all of the projections were at or below what's actually happened. If they were good at saying it could be between this and this, the reality should have been somewhere near the middle. And that's just 10 years ago. 12 years ago, I guess it is. 2012. 2002, sorry, thanks. So there's no question that the scientific methodology of the IPCC, which is really wonderful in general, because of some quirks in the system of methodology, is biased on the low side. How high will sea level rise in the next 30 years? Because that's a much more realistic time frame for cities and corporations and communities and investors and homeowners. We don't know. But we can start to talk a little more realistically about what could happen. But the truth is, nobody knows what will happen because we've never warmed this quick. And on top of that, the question of how much ice will melt this century, 86 years from now, depends on how warm it gets. How warm it gets depends on how we make our energy. Are we using coal or tar sands or nuclear or natural gas or solar? Does anybody here know the answer to that question for the next 86 years? Of course not. Nobody could possibly know that. If you can't know what the energy source is, you can't know what the heat is, you can't know how much ice will melt, you can't know how high sea level will rise. So instead of wondering why the scientists are so stupid and can't figure out the answer or arguing that it just proves their incompetence, we need to be honest about it and realize the impossibility of that question. And that's why we get ranges in publications from 8 inches to 15 feet. Now, that's actually a little extreme, I think, and I think we can narrow that down considerably. But it's an honest explanation of why these ridiculous ranges. Never happened before in hundreds of millions of years. It's never happened this fast. The last time sea level was higher than today was 120,000 years ago. And we don't know how much heat we're just going to keep putting in the atmosphere. So of course we don't know the answer. But we do know what's happening in Greenland. And in Greenland, just in the last, less than a decade here, the amount of Greenland that's in melt mode during the warmest time of the year in August has been expanding considerably. And whoops, sorry. I hope I can go back here. Yeah. This is the face of the glacier where icebergs calve off, and we know what a floating iceberg is. By the time it's an iceberg, it no longer affects sea level because it's like an ice cube in a glass. It's floating and it has no effect on the level of, just like if you watched ice cubes in a glass of iced tea, it would not affect things. You have to add more ice or take out the liquid or add liquid. But as it comes off the glacier here and enters the ocean as an iceberg, that's when it adds to sea level. But if we go up the glacier, that bending river of ice, up to the ice sheet, and we see how the sheen of water on the left there gathers into these streams, and if you if this is a close-up of that stream, you can see the steepness of the channel that's being cut. And Greenland is getting smaller quickly. Year by year, almost the converse of the sea level rise measurements. Again, is it a jagged line? Sure. Does it go up and down? Can somebody say, oh, look, it went up this year? Maybe it'll go up forever. Well, pretend it was a stock or price of gold or something like that. If something was doing this, you would know what you wanted to do, right? You wouldn't worry about the blips. And in fact, in the last 2 years, something very ominous is happening in Greenland. Not only are we seeing accelerating rates and this kind of collapse on the surface, but that dark snow there turns out to be really a serious problem. Called black carbon. It comes from soot, we call it pollution. It comes from the stoves in India burning dung and places where they burn coal and prolifically. And that carbon pollution, which can be dealt with and could slow things a little bit, but turns out has really changed the reflectance. Black surfaces absorb heat. We all know that. A black roof would absorb a lot more heat than a white roof. And it's starting to have a dramatic effect besides the temperature. And the ice sheets in Greenland are showing signs of collapse. In fact, here, pretty good shot, you can see not only the black and the pooling blue water as the meltwater collects and finds its way down to the base of the ice sheet. Here's another way to see it. Here's a major glacier. In fact, I think this is Jakobshavn, the biggest glacier in Greenland. And that light gray rock, that's being cleaned by the glacier when it used to be up that high. They call it the trim line in geology. But now the glacier's down. And you can see glaciers like this all over the world. Now here's an aerial view just showing that this is the glaciers going to the ocean on the far left. It's coming from the ice sheet on the right. And the calving, the facing, used to happen down at the ocean. And now as things warm, and I'm going to show you why in just a moment by recent evidence, the calving face is now back there at that black semicircle. And the reason that's happening, here it is in cross-section. I don't know if you can make this out or not, but I'm sorry it's tilted, but it's the way they did this. That here's what we see on the surface, that ice, but the warm ocean water, and even at 1 or 2 degrees Celsius, it's warmer than the ice and has a lot of heat content, much more than air, right? That as the warmer ocean water gets underneath what you see on the surface and looks like a glacier, it gets back and continues the melting. And now it has gone back, I can't remember, many, many kilometers. I think actually, and here we see it. There's 3 different areas that have now been mapped. This is again kind of an oblique aerial view, same orientation. The channels of water are going underneath the glacier, accelerating the melting. And this is pretty cool. This is recent radar topographic maps showing what's beneath the glaciers. And we didn't understand this until very recently. And it's starting to explain why things are becoming unstable in Greenland. We thought Greenland was a ring of mountains, kind of shown there in white, that would restrain even extreme melting, and that the meltwater would have to get out through the valleys, if you would, in the rock, and that was a constraining force. But it turns out, by this very latest, this is within a couple of years old, there's a huge channel in the upper northwest, and it looks like that's where the meltwater is going out. But worse than that, the warm water is getting in there and destabilizing. In an article published just a couple of weeks ago, there's also signs that the one area of Greenland that we thought was not doing too much, that was pretty stable, the northeast, that too now is showing signs of instability and potential collapse. Those things are really dynamic. They can change from year to year. But we now have enough information to understand why Greenland could be worse than what was forecast in the IPCC with its very conservative methodology of saying what do we know would happen that we can quantify. So there's a big valley in the middle of Greenland. In fact, to put that size of that valley in context, it's about the same size as the Grand Canyon in depth and square area. Huge. Antarctica. I know this has really got you excited, right, so far. This is a little scary and depressing, and bear with me. I'm going to try and give you the glass half full of this story when we get done. I know this is sobering, and I certainly don't want to make light of it, but we've got to look at this realistically, just as we do with other crises. And I think most of you are probably of like minds, I hope. West Antarctica. So let me give you the last bit of bad news, and then we'll talk about what do we do about it. As I showed you before, and it's again shown in red and yellow here, that's identifying where in Antarctica the glaciers are moving the fastest. And a similar situation, here's a cross-section of these huge glaciers that are called submarine because they go underwater. And there's only a few of them in Antarctica that do this, but they become more susceptible to the ocean warmth again. And there was this grounding line. It's actually about 300 meters tall, I think, about 1,000 feet, if I remember right, as that kind of peak. That's been the restraining line, and we just didn't know enough about it. But now they've put submersibles, ROVs, underneath there, and really can observe it and do some measurements, and find that the meltwater has gone much farther back than anybody thought. And more than that, they've now calculated that at the current rate of thinning from the atmospheric thinning at the top to the marine thinning underwater, that when they calculate the grounding line and the speeding up of the glacier, that it could clear the grounding line, that pinnacle of rock, in about 20 years. Now, that's new information. We really didn't have a way to quantify that before. That would indicate that on the current track that we won't get anything catastrophic in the next 20 years. Because that set of those couple of glaciers right there are the possible cause of catastrophic sea level rise. That one region of West Antarctica could account for 3 meters of sea level rise. Now, if you remember right, all of the other stuff combined was just under a meter. And I think you now know why the report says it's not to hide things, but they follow their own rules. What do we know will happen that we can quantify, that we know will happen this century? Maybe that'll hang around there till next century. It's possible. But we've also have to be realistic. So we now have the mechanism, we have the measurements, we can see beneath the ice and actually begin to talk about with very realistic scenarios of, how bad could it get, how soon? Because the water now stretches back 40 kilometers from the sea. That's a big deal. And the last shot of Antarctica before I kind of finish, and we'll get into some questions and talk about this in just a minute, but just it's worth comparing what we see from the surface, even with the markings of melting. But now we know what's underneath Antarctica, a very different depiction than what I showed you from Greenland, but comparable in some ways. This is showing us not the elevations and the topography so much as where is there land underneath Antarctica. And the importance of that is that East Antarctica is really much more based on an island, although it's effectively a group of islands. And the problem with those glaciers that I've talked about is they really do go deep underwater. They're not supported on land, so they're exposed both to the marine warming and the atmospheric warming. One of the charts that's been bandied around in the last year or so is by either people who are confused or trying to confuse or just misinformed that the warming has slowed. And they often say, well, for 17 years the warming has slowed. And there's some ways that that's true. But this graph of temperatures for the last 40 years, I think, puts it in very good perspective. If you want to pick the right sample of years, you can get a temperature line which is flatter going down. And so they're right. If you go back here to 2003, boy, temperature hasn't been going up. It's flat, right? Or down even. And it happened again before that. And of course, you can see the red line here, though. If you look at the big picture of 40 years, you have to decide. Do you want to look at the 6 short lines that are all flat or going down? Or do you want to look at the red line that plots the trend over the 40 years? So it's a classic thing of lying with statistics. If I can pick my sample, I can probably get you to buy anything. Buy this investment, look at the last 17 weeks or this 17 weeks. of course, anything can look like anything we want it to. That's why it's always good to take even periods of time, decades, centuries, thousands of years. You see things with a lot more objectivity and lack of bias. So the takeaways, if I may, are that we have to combine storms plus extreme tides plus sea level rise to see what's going to threaten and inundate any coastal area. And it's not just coastal areas, it's areas on tidal rivers. That could be up the Fraser, it could be Sacramento, 80 miles from the Pacific Ocean, capital of California. It could be Washington, D.C., Hartford, Connecticut, any city on a tidal river, up the Hudson, 100 miles. Those cities are all directly affected by sea level rise. After years of stability, the 6,000 years that sea level hasn't changed much, it's now moving. And it's moving in the wrong direction if you just want to look at the natural cycles. We can slow it if we do the right things to deal with greenhouse gases, but we can't stop it. It's unfortunate. I'd like to tell you there was a way to stop it, but there's enough heat in the ocean, almost 1 degree Celsius, that the ice has to get smaller. There is no physical way to stop that, any more than you can stop an iceberg from calving off a glacier, or stop a tornado in its path, or stop a tsunami. Those physical functions do not lend themselves to technology to stop them. Now, we can find technologies to make energy without carbon, or reducing that. We might even, if we're good enough, create such cheap and abundant energy that we could somehow cool things down to where they are, get the CO2 out of the atmosphere. That would be great. Return ourselves to the 350 parts per million. We're about 400 parts per million now. And back down to the historic level, the range of CO2, that green up and down chart I showed you earlier, was 180 to 280. I probably didn't say that. But we're at 400 now. We're 40% higher than in the last 10 million years. There's no way to dissipate that quickly. I'd love for there to be, but there isn't. We have to think of this like going to the doctor and hearing some bad news. You've got a disease. Or you went to your investment broker and say, I'm really sorry, but that investment fund we put your money in disappeared, right? Stuff happens. Go to war, come back an amputee. It's terrible. But life throws curveballs at us. But if I'm to find a glass, the proverbial glass half full as opposed to half empty, and this is certainly a glass half empty at first glance, but here's the 3 ways that I, for myself and my 13-year-old daughter, and family and friends and everybody, and people I know, and many of you are friends in the audience, is we've got to find a positive way to look at this, just like any other challenge we're faced. And the 3 positive aspects of this to me are that most terrible crises like tsunamis and tornadoes and earthquakes and all those things, war, bombs, whatever, we have no preparation for. This is a bigger problem. It's predictable. It's essentially permanent. It's going to go on for centuries. And we can see it coming decades in advance. How good does it get to be told that something is going to change, that's going to change the shape of where you live slowly, and that you have decades to plan and prepare for it? In my book, that's a pretty good deal. Sounds like a joke, but it's not. Second thing is, we do amazing things when we focus on a problem, whether it be putting a man on the moon or fighting cancer or AIDS or anything else, right? And if we really focus ourselves on adapting to higher sea level, which is going to rise, and move our shorelines inland, we'll do some neat stuff, architecturally, engineering-wise. But as long as we're confused by 10 to 32 inches or 26 to 82 centimeters, we're not focusing on the problem. We haven't even trained our architects and engineers yet. One of the things that I've suggested is we should start thinking about a meter of sea level rise. As I do consulting for communities and corporations and investors now, and help them see how do we plan for this. And one of the things that I've come up with that a lot of people really have latched onto is say, let's stop wondering how quickly it's going to happen. That's the wrong question. We don't know. Let's start preparing for a meter or 3 feet of sea level rise. knowing there is no current way to say whether that happened in 2100 or 2050. But the sooner we begin planning for that, changing our building regulations, challenging the architects and engineers, we'll come up with some cool stuff. Now, it's difficult because it's not just raising one house or one office building, it's the drainage system and the street levels. But the longer we delay it, the more we put up buildings that are down there at the current level. It's a huge change. But I've talked to a major engineering firm here in town this week. I've talked to big corporations and governments in the Bay Area and in Florida where I live, and people are getting their arms around there's a lot of merit in saying, okay, whether it's 40 years, or whether it's 30 years in a terrible case, or 130 years, let's start thinking about sea level being higher. And a meter is a great distance because it's a huge challenge. And after that meter, we'll learn for the next meter. But if we keep thinking incrementally, what's going to happen this 5 years in our 5-year plan, how many inches, we're not going to do anything. There's nothing to design for. So planning for a meter of sea level rise is kind of my new mantra. And mantra is not the right term, excuse me, but guideline or way to plan and conceptualize this. And it's actually taking hold in a number of places, and it'll be kind of the core theme of the next book I'm writing. But we can slow sea level rise but not stop it. That's the unfortunate truth. But the sooner we embrace it and confront it and deal with it, the better, like most problems. Inches matter, whether it be breaching a dike, getting over the threshold of a door jamb of a shop or a restaurant or your home. Okay, inches matter. And again, the base sea level is added to with the extreme tide or a storm surge. That's the other thing that's kind of insidious, because we see the big storm surge, we see the monthly extreme tide, and that little bit of sea level rise you never see. But it's the tortoise that's going to win the race, if we go back to the kid's fable, right? It's the steady and unstoppable and irreversible sea level rise will eventually be greater than the storm surge or the extreme tide. But you don't see it now. In cases where you have exposure, whether it be houses, businesses, communities, you've got to start thinking about risk, just like we do anything else. The average home in North America has a 1/3 of 1% chance of having a fire in any one year, sufficient to call the fire department. Think about that. It's 1 chance in 300 that your house or condominium or building, on average, will call the fire department with that severe a fire. So if 1 in 300 doesn't bother you, cancel your fire insurance and get rid of those pesky smoke detectors that sometimes go off in the middle of the night. It's not a problem. It's 1 in 300. But of course, 1 in 300 chance of being engulfed in flames is serious enough to do something about it. And if the chance of serious sea level rise rises to 3% or 10%, that's a serious risk, because a meter of sea level rise is a game changer for every coastal community in the world. And again, we're not thinking of it in the right risk terms, and people need to start asking that question. And finally, for people, you can look at this in economic terms, and what do you do for your property? If somebody's perhaps old enough, says, well, I'm not going to live more than 20, 30 years, or even people in their 90s say, I've got 3 or 4 more years. What the hell? It doesn't matter. I don't care. I can't do anything about this. And then I remind them of the other way to look at this, which is that for the first time in human history, we now see a different planet. And interestingly, the real important line is where the ocean and land meet. And it's great, and I really mean this sincerely, that the Vancouver Aquarium has thought and taken the interest of John and his staff here to expand this beyond looking at just the critters in the ocean, the fish and the mammals and the great things that are in the Vancouver Aquarium, but to educate people about this ocean planet. And it goes a lot beyond the biosphere, what's in the water. And telling people the story about the ocean and where it meets the land is kind of a new message for aquariums, I think. But it's another way to engage people to think about how is this ocean planet changing. And I can't think of any more profound way, because it's going to affect our real estate. It's going to affect our investments, our communities. And we can either punt, ignore, bury our heads in the sand, pretend it won't happen, or we can do something about it, like most problems. Of course, unfortunately, it seems that today most problems just get ignored and kicked down the road, and politically, at least in my country, south of the border. But I think some of that up here too. John?
2 questions.
Yes.
So your book came out a year and a half ago.
Yes.
And you've been talking to lots of audiences.
Yes.
So are you seeing a shift in people being interested, concerned, even willing to consider the idea? You talk to engineering firms, you talk to city planners. Or even in that year and a half, are you seeing a shift? And do you see a vastly different take on your message in different parts of geography? East Coast, West Coast, US, Canada, whatever?
Good question. So John's 2 questions, if you didn't hear them, and for the they're streaming this, so for the others. In the year and a half, or since October 2012, that I've been doing this circuit and explaining this, both in presentations like this, but in more in-depth briefings for certain people that want to do that. Do I see a shift in it? I would say yes. I think, though, by coincidence, the week my book came out, which is the week Sandy hit New York and New Jersey, which is pure coincidence that it happened that way, was probably the turning point. And it wasn't sea level rise, but seeing those shores of New Jersey breached and seeing cars floating out of New York tunnels just got people to say, wait a minute, this is like unreal, and what could happen beyond this? Could it happen again? And I think that was the turning point. And most people dealing with this, I think, believe that was a turning point. So during the last year, this subject is so profound and unprecedented and sobering that it takes people sometimes thinking about, and even some people tell me they've read my book twice and they've listened to it on audiobooks, because it's a lot to get your head around. And I think this is one of those game changer view of the planet. It's almost like DNA was when John and I were about the same age, that discovery that kind of explained a lot of things in biology, or plate tectonics generation before us, seafloor spreading. This is one of those things that really changed your view of the world. And you don't do it in one sitting. You may get it, but you got to kind of think about it and come back to it, because it really does change your view of the world. But so I'm seeing more and more interest. I'm getting more and more requests to speak. But we're still just, I'd say, at the tip of the iceberg, because, no pun intended, but even with attorneys who are very good at analytical thinking and getting the argument, and engineering firms and architectural firms, they may be aware of pieces of this, but in fact, none of them have understood the profoundness of this, the permanence of it, and the fact that the official figures are on the low side. I have not found one group yet that said, no, I really didn't understand that. Everyone says the opposite. They say, I knew something about this, but I had no idea why the 26 to 82 centimeters was low, or what's happening in Greenland or Antarctica. This is the current, this is coming out. Every week I read the latest science journals. Tough stuff to read, the peer-reviewed literature, but this is the latest stuff. And so I think both are happening. I think there's a growing awareness. I think it did change with Sandy, but this is so profound it's going to take us a while to digest it and then adapt to it. And the fact that you're out here tonight, credits to you for taking the time, spending a few dollars, and patronizing our great aquarium here in Vancouver, but to find out more. And I think we have time for a few questions.
Yeah, I wanted to go ahead and jump in here, and just raise your hand if you'd like to ask a question. And if you'd like, you can either repeat the question, or I can walk over and hold the mic to our
I think
audience.
it'll be faster.
Okay, so why don't we just make
We've
sure
only
we
got
repeat
20
the
minutes. They're going to
questions.
turn the lights out here in 20 minutes. So literally, we have 20 minutes to be done.
Okay.
Yes.
I have 2 questions.
Okay.
With 3 feet of sea rise,
Yes.
will there be, or is there any understanding of what the impact will be on water supply as the ground rises? First question. And the second question is, it's a complex subject. If you had to come up with a headline and a subhead that you could use to get people interested to find out more, what would that headline and subhead be?
Two great questions. Okay, the first one is, does 3 feet of sea level rise affect the fresh water table? To give you an extreme example, in Florida where I live, which is pretty flat and it's porous limestone, and the water, freshwater lens sits on top of the seawater, which permeates the rock underneath, just about 8 inches of sea level rise will destroy the fresh water table, what they call saltwater intrusion, or begin to. It's a very serious problem. And again, it depends upon geology, the rock form, and the profile. Okay, but less than 3 feet can do a lot of damage to the freshwater table, depending upon the geology. The second question about the headline and the subhead, how would I get people's attention? I think it's something like, the shoreline is moving inland for the first time in 6,000 years. Find out, why, what could happen, and why the official estimates are low, or something like that, might be. Does that help? Yeah. Great. Yes, sir.
Given a 1 meter rise in sea level, what would be the reduction worldwide of land masses?
Oh, I think in percentage terms it's really small, surprisingly. And it varies a lot. I mean, the southeastern United States, which is much more gradual, will disappear much quicker than the western North America in general. But again, it has to do with the elevation profile of each area. San Francisco Bay, for example, as an extreme anomaly, has a unique problem that over the last several centuries, they filled in the bay to make cheap real estate. They only had to put about 10 feet of fill in there, and they got another acre of land. And they've done that for 250 square miles and created some very valuable real estate. And when they started doing that 150 years ago, they brought it up about 2 or 3 feet just above sea level. Now they realize that when sea level reaches there, the entire city of Foster City and Redwood City and all those other places are going to just flood at once. And they have a real vulnerability. And it gets into Silicon Valley as well. Yes?
Can you discuss the issue of ocean acidification and its positive feedback loops with carbon being released from the water?
Sure. The question is, what about ocean acidification? How many of you have heard of ocean acidification? Oh, boy, you've got a very smart group of members and followers. As you know, ocean acidification is actually a decrease in the alkalinity of the ocean pH, just like any scale. Fresh water is 7 in the middle. The oceans used to be about 8.15. They're slowly coming down, but it's a logarithmic scale, like earthquake measurements, if you will, and 0.3 change in pH is huge. Actually, 0.1 is a 30% change in pH. It's huge, and it's happening, and that's why the shellfish industry is already battling that. It's caused by the same thing as sea level rise, which is ultimately the carbon dioxide in the atmosphere, but it's not through the same warming phenomenon. It's a different phenomenon. It's that the carbon dioxide, that original source problem, putting up CO2 in the atmosphere, the carbon dioxide dissolves in the water and becomes carbonic acid, and it's a direct form. It has nothing to do with the temperature. So both the temperature and the carbon dioxide, or the acidification, are coming from the carbon dioxide. Did that answer that question?
Let's go ahead and take one more question.
Okay. Maybe not. There might be another question. One more question. No? Well, this is great. We've answered the questions. They haven't turned the lights out yet. Thank you so much. You've been a great audience, and I appreciate your interest in this very important subject.
Thank you, John. Thank you. So just in case you're worried, it isn't that the aquarium didn't pay its electrical bill. It's that with the construction going on, finally, in a 58-year-old building, our electrical systems are all going to work together after tonight and one more shutdown. So this is a planned shutdown of the entire aquarium so that electrical engineers can hook up new equipment in the old building and the new building, which is something we're all delighted with, because we can worry about earthquakes or we can worry about all sorts of things, but having your building catch on fire from faulty wiring will be taken off the table. So it's great for us.
And I said it up front, but I really want to give acknowledgement to John and Jonathan and Dolph and the staff here. Not only are they upgrading the aquarium physically, but their idea to outreach and stream this kind of information, to take information about the oceans and what they're doing physically here with the animals and the marine life and broadly, but also information like this, I just think is really leading stuff, and you're to be complimented on that kind of vision. the world needs to know more about this ocean planet, and when they think of an aquarium, you tend to think of the critters, but understanding how we interact with the ocean, and even to the point of what does it do to our shoreline, is certainly on the leading edge thought of that, but I commend you and appreciate your doing that.
Thank you.